Since radicals tend to be complicated, tend to be scary, intimidating, let's analyze the transformations of the parent function of radicals. On a screen, we see the square root of x. And as we know, the square root of x, the parent function of the square root of x, and of the radicals of even index radicals, is going to look like this. Of course, sometimes it's a little bit more stretched, a little bit bigger, a little bit smaller, but for even index radicals, it looks like this shape, this curve going upwards. But because it's more complete and the transformations are the same, let's analyze the transformations of the parent function of an odd index radical, like the cubic root of x. The reason why we're going to do the transformations with the cubic root is because the cubic root is more complete. It has the full graph. Although the transformations will be the same, because as we learned, if we have a positive a or a positive constant outside of the radical, this is a vertical transformation going upwards. Positive means upwards. Positive outside of the radical means upwards. Then, using that logic, if we have a negative outside of the radical, that means downwards, because vertical transformations, they keep the same sign as the operation that is being applied. Let's bring our graph back to the original position, because now let's do the horizontal transformations. If we have a positive a inside of the radical, we need to move to the left, because inside of the function, any operation inside of the function is a horizontal transformation, and we always do the opposite direction of horizontal transformations. That's why positive a means we go to the negative. Let's bring back so we can do the other transformation, which is a negative a inside, so we move to the right, because horizontal transformations every single time, they represent the opposite as what the operation is saying. That's why if we have a negative a, it means we have to move in the positive x-axis or to the right. And let's go back to the origin one more time, because the next transformation is when we have multiplications. And multiplications is stretching. So our graph gets vertically stretched by the same amount of the number or the constant that we are multiplying our function by. So if we're multiplying by, let's say, 5, we're stretching this function by 5 using the same logic we have been doing throughout the whole lesson 5.3. Then a division is a compression, because the transformations are the same for every parent function. The only thing that changes is the shape, because the parent function dictates the shapes that we are having. The last transformation we have is when having a negative. Let's bring our negative in front of the radical, and that negative just means a reflection about the x-axis, or vertical reflection. So our graph looks like this. So basically we treat the x-axis as if it was a mirror. So let's take the negative out so we have the original. And to finish up, let's go back to our x squared situation, because we did everything for the x cube, for the cubic root. But let's go back to the x squared. And the reason we want to go back to the x squared is because there is a transformation that is not much visible with odd index radicals. It's better seen if we use an even index radical. That means we need to erase the left part of the graph, because remember, even index radicals don't have that left part. And the transformation we're looking for is when the negative is inside of the radical. When the negative is inside of the radical, we have a reflection about the y-axis. So basically, we need to treat the y-axis as if it was a mirror. So instead of looking to the right, this function looks to the left. With this, we finish the basic transformations of parent functions. Of course, there are more parent functions and there are some other transformations, but these are the most important that will give us the head start for this topic in algebra of graphing and transforming and sketching functions.